Um, okay, I think I can start. Hello, everybody. Thanks for joining us for this talk. In this talk, we are going to talk about the practical demystification of CRDT. I'm Nami, he's Dmitry, and Didier also had a great contribution to this talk, but he couldn't join. The first disclaimer is that, okay, we are not hardcore academia guys or from academia, or we are not very hardcore distributed system guys, but we want just use some academic achievement for solving a real world problem. Yeah, this is us. So we do everything, and developer in this project in TomTom. It's a full stack developer doing from this front end to the back end, and also handling the infrastructure. The project that experienced this research is called NavCloud. It's a cloud-based storage service to allow users to seamlessly synchronize trip information between devices, as well as TomTom website, which then you can have your navigation information like favorites, active routes, destinations, all those things, and you can have it everywhere. And TomTom has a lot of customers, of course, and and a lot of devices in the market. All of them gradually will be enabled by NavCloud. So the project should be, the service that we provide should be scalable and available. And because of the these are sensitive information, especially the location-based information is one of the most sensitive information. We have to be really secure and also compliant to the legal requirement. And also because this is a service and it's going to be used in the third-party application, we have to be reactive and do not degrade their performance. These are the technologies that we used on the server and the client, Arca, Spray, Scala, and we deployed on Amazon Web Services, and also we built different set of client libraries to let the clients integrate with our services. This is a nature of the many synchronization. These are the natures of the many synchronization systems. In the ubiquitous computing era, all the connections are really unstable. So you can be disconnected for most of the time. You traveling in the tunnel, you're going somewhere in the farm, you don't have coverage, and you lose your connection. In TomTom case, also TomTom provides SIM cards in some of the devices, built-in SIM card, and it paid for that SIM card. So, but these SIM cards should have very low bandwidth, otherwise they will be really expensive. So your bandwidth also really limited. So the data that transmit with the server and client should be really packed. Compacted actually, and also because you are most of the time offline, user doesn't want to wait until you get the connection to change the stuff. They want to be able to do things in offline mode. Oh, and the result of this is to have changes which are concurrent, and those changes can be in the conflicting states. Of course, in this system, there is no guarantee for the order. The user doesn't expect any data loss, and user expects that the data converge to the state that he most probably expects. How to deal with this nature? Of course, you can build a lot of logic all over the place to handle this. I doubt about that, but if you also be able to do that, it's really will be unmaintainable code. But as Linus Torvalds said, actually, the good developers mainly solve the problems with the data structures level, because data structures abstracts a lot of things from you and can handle all of those logics out of the box. That's the reason that we went we decided to use CRDTs. As I said, CRDTs is a data structure, it's a data type. It has its own algebra. And it's meant to be distributed. So each CRDT instance can have a lot of replicas all over the place, and all of those can be out of sync at some time, and even in the conflicting states. But CRDT knows how to solve the conflicts, and they all will converge to a correct state. How CRDT does this? The main ingredient of doing this is actually a merge function. Merge function is a binary operation between two CRDTs yielding another CRDT, which must be commutative, associative, and idempotent. And I assume that these are clear characteristics. And why does this matter? Because apparently these characteristics is a good match to the distributed systems characteristics. For example, in distributed systems, order is not guaranteed. And of course, you can receive events in a different order. But the good thing is that if you receive something from the client and you're just merging in your node, whatever client or server, you have a local state, you receive something from the network, and you just merge. If your merge function is commutative and associative, it doesn't matter in which order you receive those events, because merge function is commutative and associative. And even also in a distributed system, you receive events more than once. Because imagine I send you something, you send me back acknowledge, the acknowledge it will be lost, and then I have to again send to you. So you receive twice. But if the merge function is idempotent, it doesn't matter. It doesn't harm. I just again merge it. And in practice, CRDT is not for just servers and nodes in the cluster stuff. It actually gives the user a very good experience. Because if you have CRDT everywhere in the distributed systems, then you can do local changes. And local changes means that user doesn't need to wait until it gets connection. So it can do offline changes always that he wants. And CRDT will promise him that everything will converge to the correct state. Example is that imagine that you want to count the number of the hits on your website. So this counter is always growing. And G counter is one of the data structure that actually is always growing counter. One way to solve this, imagine that your website is really successful and you cannot count the number of the hits on single machine, and you need to distributedly count the number of hits on your websites. What you can do, you can have a fleet of machines, and each machine counts separately, and for example, this one counts till now 5 times, other one 6 times, and at sometimes they are starting gossiping with each other, and then just add all the value together and reach some value. So imagine that the 3 machines that we have, one counts 6, one 5, one 4. I can sum up all of them, 4, 5, 6. Is it going to work? No. Why? Because addition is not a CRDT compliant operation. Addition is not idempotent. So upon the gossiping, if I receive your value twice, I will count them twice. And this is wrong. So the solution is that you can define an array of values, which each element is corresponding to each node. And each node only increases the element corresponding to itself. And upon gossiping, they just pass these arrays together. And each machine, whenever receive value from other machines, it just picks the maximum of the corresponding elements. So for example, in this case, there's ABC, so our array will have 3 elements, A, B, C, and each of them, A increased A1, B increased B1, and upon gossiping, for example, C will receive the current value from the B and A, and it just picks the maximum of the corresponding elements. So the result in this case, for example, will be A6, B3, and C9, and the total value will be the sum of them. This one will work. Why? Because unlike add, maximum is CRDT compliant, because maximum is idempotent, associative, and commutative. Another example is gset. Gset is always growing set. You get the element and you just put it inside your set. In this way, again, the first solution comes to the mind is that, okay, you have a different machines, and whatever you receive, you just update your local set, and upon gossiping, you pass these sets together, and each machine, whenever it receives sets from others, they just union them. Is it going to work? Actually, yes. Because unlike add, union is CRDT compliant. Union is associative, idempotent, and commutative. So for gset, it's even easier. You just have a local set, you just add it to that, and upon some intervals, you just merge them together. So, and this is the reason. So let's see that whether this one can solve our problems in NavCloud, the CRDTs. In NavCloud, we are synchronizing different navigation informations. One of them are favorites. You go somewhere, you like it, you mark it as a favorite. We also sync other things like routes, like a point of interest, and a lot of other things. But it is an example. And each favorite has different attributes, like longitude, latitude, name, and other things. The naive approach of synchronizing things, because you may go to the parking and like that parking, you want to set as your favorite, but at this moment you don't have connection, so you will send this data a little bit later to the server. But user doesn't want to do that. You want to just set it, and finally it should be synchronized. Of course, there's a naive approach. Okay, the device tried to connect to the server, and if it is successful, so it's just send it to the server, and server using last write wins. And if it's not successful, just try again until it gets the connection. And of course, it's not going to work, because last write wins. it has a lot of situation that you can have concurrent changes, and actually your changes which happened before reach a server after. So actually the result will that the stale updates will win. And you don't want this, and user really doesn't want that. And you see in very many synchronization systems these days that this actually happens. So what? Let's try to see that whether CRDT is a good match or not. You already saw this slide. This is the characteristics of the NAV cloud and many synchronization systems. The connection on unstable, CRDT doesn't care at all, because it says that I can do local updates, and whenever you have connection, I will just propagate the state and it will merge, I promise you. Bandwidth is limited. Of course, there's a two-way of CRDTs. There's operation-based CRDT and a state-based CRDT. In a state-based CRDT that these talk mainly is about, nodes should sense the entire state every time that they want to gossip and reach the total state. So this is not very bandwidth friendly. What we did, we extended the algebra of CRDT to add diffs to that. And we only sense diff over wire. And this is really, really bandwidth friendly. Of course, the third bullet about offline update, of course, CRDT is really good for that. Concurrent changes, CRDT says that it can solve the conflicts. Order, the merge function is associative and commutative. No data loss, of course, we never override, we always merge. And data convergence. Okay, why data will converge everywhere? That's the question. So I merge here, I merge there, I merge there. Why they are going to converge to the same value? Because we use the same merge function everywhere. We use the same merge function in client, in server, and even in database. So as an example, we use RIAC as our backend database, as a data store, key value data store. It's a masterless, RIAC is a masterless key value data store inspired by Amazon Dynamo article. So what RIAC does, whenever you write to the RIAC attach something called vector clock to that value. And whenever you can just don't think it as a vector clock, let's say tag. And whenever you read back that value, you will also read that tag. When I read the value and I read the tag, if meanwhile something happens on the database, the tag will change. If I write back to the database, I will write with the stale tag. And RIAC, in this case, doesn't override the existing value because it said that your tag is stale. If you configure that, it keeps both value as something so-called siblings. And this is a responsibility of application that upon read, just merge all those siblings, resolve the conflicts. But for us, it doesn't matter. We have a lot of CRDTs saved on the database as siblings, and we just read them, merge them. On the client, we use the same merge function. On the server, we use the same merge function. So we know that these merge because of also the commutative, associative, and idempotent, and they all will converge. So that's really simple. It's just 2 lines of code for us, and not that much logic. This is, I think, yeah, this is, yeah. So this is a little bit of introduction and the theory, and now Dmitry is going to explain exactly how we implemented these things.
Cool. Thanks, Nami. So, yeah, exactly. Let's try now to implement a CRDT set that will meet our needs. So, what are our needs, actually? So we want to have a replicated collection of favorites that will allow us to add elements to that collection on different replicas, to remove elements, and to have a more or less efficient way to mutate elements in that collection. And as Nami said already, footprint of the collection, the data that we are going to send over the wire, we expect it to be reasonable because we have network bandwidth limitations. So we started looking at the CRDT research papers and different options that we have to implement a collection. So the first one we looked at was a 2-phase set. So it's a set that does support addition and removal operations. And it can be modeled as basically just 2 G sets, 2 grow-only sets. In one you store added elements. In another one you put the elements that you want to remove. So it always grows. And the removed elements in that case, they also can be called tombstones. Let's have a look at an example. So we have 2 replicas. They both store 2 G sets each with some elements. So if, for example, you want to remove an element, exactly you take, for example, a cat on B node and then just move it to remove set, right? So how do you merge this data structure together? So what you need to do, you need to merge two G sets, two add sets together, and two remove sets together. And we already learned that G set actually is mergeable, right? It has a merge operation. It's just a simple union. So that will be the result of the merge. And how do we calculate the lookup of that collection? So what is stored there? What are the elements? We need to find all the elements in the add G set that are not in remove set. It's deadly simple. And here is some code how you do that. Exactly lookup, add set, diff, remove set. That's it. And then for merge, it's just a union. It didn't work for us for two main reasons. So one is that if you have removed an element in two-phase set, it's gone forever. You cannot re-add it back. That's the first thing. And the second thing is that elements are immutable. So one might argue that, of course, you can model your modification operation as simple just removing current value and adding a new one. But if you do really updates frequently, for example, then your remove set, the set of tombstones, will inflate really fast. And that is going to bite you, might going to bite you. We will have a look at that a bit later. So we started looking at the other options. So there is a last write wins element set. So you can think like last write wins. We thought that we said that it's not really, it's quite a naive approach. So let's have a look how it works actually. So it actually works in a way that to each element there is additional metadata which is added. It's a timestamp. So it can be modeled again as two G sets, one for added, one for removed elements. Each element now is a pair of timestamp and a value. And in that case, it does support re-adding of the elements. And how you do that? You just need to add an element with that value, but with a higher timestamp. So let's clarify with an example. Again, two replicas. Each element is a pair, as I said, of timestamp and a value. And how do we merge this data structure? It's, again, the same technique. We have two G sets. We just need to merge the counterpart, the add sets, and remove sets. That's it. And the question is, that's the result. And then how do you calculate the lookup? So to calculate the lookup, actually, you have to find all elements in the add set that have a timestamp higher than the counterparts in the remove set, if there are any. And in that case, all elements have 1 because the timestamp of addition was higher than the one in remove. And here is exactly the same predicate that you can encode. We will share code samples later. It didn't work for us still. And the main reason is that the elements are still immutable. So you have to do the same procedure of removing, adding back a new updated value. So there is another variation which is called OR set. It stands for observed removed set. So OR set solves the problem a bit differently. So it actually adds additional metadata, which is a tag, unique tag associated with each element. Again, it can be modeled as two G sets for additions and for removals. And it also does support re-adding of elements. So if you have a value that is stored with a particular tag and remove set, the only thing you need to do is to add that value back to the add set with a different unique timestamp. Here is an example. So each element is again a pair. In this case, it's a unique tag, like for example, C and cat. And then, so how do we merge two replicas together? Again, exactly the same techniques. We have two G sets. They are mergeable. We just take a union of them. What will be the lookup in that case? So in order to calculate the lookup, we need to find elements in the add set that have a tag which does not appear in the remove set. And in that case, again, all elements have 1 because all values have at least one unique tag that is not in the remove set. Yeah, and there is a code sample for that. Again, the merge is exactly the same as previous sets. It's just a merge, a union of two add sets, two G sets. So it doesn't work for us still. Same problem, immutable elements. So exactly the same procedure for mutating elements. So now we started thinking like, can we tweak a bit the existing solutions to meet our needs? So can we extend the existing CRDT set with this updated functionality? So we came up with this observe updated remove set, or in short, our set, so pun is intended. And actually, this set stores additional metadata per each element, so it has a unique identifier, same way as we had with unique tag associated with each element. And unique identifier is an identity of an element. So it's an immutable identity which is there forever. And there is a value associated with the element as well, which is mutable. How do you mutate the value? So if you want to change a value, you need to preserve ID. You need to update timestamp and update the value. That's it. So another trick that we did was that instead of using G-sets, for example, we use just one single underlying set that stores both removed and non-removed elements. It's just a simple optimization. And in that case, we have a sort of discriminator field, remove flag. So if it's set to true, then an element is removed one, right? And if you want to remove an element, you just need to update that flag. You need to increase the timestamp, and you are done. And of course, this underlying set can contain only a single element for the particular ID. IDs should be unique. So here's an example to clarify that. We have two replicas. So each element in these replicas is actually consists of 4 fields. So ID, then timestamp, then the value that you want to store. It can be a more complex one than just a string. This is just an example. Then an optional discriminator remove flag. So how do you merge them together? So in order to merge these two sets, you need to take a union of them, then take a union of all elements. Then you need to group them by unique ID. And in each of these subgroup, you need to find a winner. How do you find a winner? Well, you have a timestamp. So you can pick a winner by timestamp, for example. In that case, we identified the winning elements. And how do you do lookup in that case? So for lookup, you need to take the elements which have remove flag set to false. Pretty simple, right? And here is some code, exactly taking union of elements, grouping them by ID, taking max by timestamp. That's it. So okay, so we have this model of our set. So let's apply that to our use case, to have a replicated collection of my places. So we have this additional metadata that has to be added to our domain-specific object, which has fields like name, location, and etc. We add this metadata, which is ID, timestamp, and remove flag, and we wrap it into sort of element state object, in that case, favorite state. So one might argue, okay, so you mentioned that we do max by timestamp. So what happens if we have exactly the same timestamp for values? Yeah, that's a good question. So actually, comparing timestamps is not enough. So you have to compare the whole element structure. So what do you do? So first, of course, you compare by timestamp. If you have a tie, you check the remove flag. And in that case, you have different bias. You can have an add bias or remove bias, depending on your actual use case. And then you have to compare the rest attributes. It's important that the compare function is deterministic. So you cannot just pick a random value. Okay, you think that timestamps are the same, I don't care, right? No, it has to be deterministic. And that's important also because merge depends on that. For example, what you can also do, you don't want to compare all the fields in the value one by one. You can just take a hash of the value, for example, and then just compare 2 hashes in lexicographical order. In terms of determinism, it's fine. So, okay, now we have this nice and shiny, as Nami explained, the structure where we have CRDTs everywhere in different layers in our SDK client, server, even a database layer. And the model basically is like, in all the layers, you operated with this merge function when you receive, let's say, updates from other layers. And then if you want to send something, you just need to calculate a diff and then that. It's pretty unified model to think of, to reason about, and also to program. For example, yeah, if your server node, for example, receives an update from a client replica, what does it need to do? It needs to get the local replica from database layer. It needs to merge it with the client and then store it back. And then if the database layer has a conflict, exactly as Nami explained, we will also solve that separately. So in all layers, the flow algorithm is the same. So now you can think like, okay, it solves all the problems, so is there any trick? Well, there is kind of always a trick, right? So let's talk a little bit about like downsides, or at least the considerations that you have to take into account. So I think the most common question that we've been asked about is when people hear about CRDTs and we're using them in production, they say like, so what do you do with garbage? So let me clarify. So CRDT set tends to grow because of tombstones, these deleted elements marked in the set, right? And it's kind of, it can be unbounded growth. And we already had, we heard a nice talk yesterday about building stateful distributed services that unbounded data structures like a killers of distributed services, and that's complete true. So what are the options? So one thing that you can consider is like, yeah, well, of course, you need to prune the deleted elements, right? So the question is when. So intuitively, you can think, so I can get rid of this tombstone if I'm sure that all the replicas that hold the CRDT set actually have observed that tombstone. If it's not the case, if you have a partitioned client for a long time, and you meanwhile remove the tombstone, then it goes back online. It will resurrect that tombstone, and you are back in the same situation. That's pretty bad. So one thing that you can kind of consider is using some sort of time to leave for tombstone rule, where you basically put a sort of a threshold on the lifespan of the tombstone and saying like after some time I want to get rid of it. It's a reasonable approach, but it's also a tricky one. You have to apply this rule independently on all the replicas. Otherwise, you will have exactly the resurrection case again. Yeah, and it's a bit not that flexible. So another canonical way to get rid of garbage is to use a bit upgraded versions of CRDT set, which are replica-aware CRDTs. That's what researchers suggest in CRDT fields. We don't use that because it's sort of a trade-off in your system, in your APIs. If you want to introduce a replica awareness, you are sort of kind of making your API harder to work with. So there is always a trade-off. So another way to mitigate the impact of growing sets on on functioning of your system is to use diffs, as Nami explained. So we extended the algebra of CRDTs with diff operation, and yeah, probably you can think like if the client creates and updates a couple of elements in its own local replica, it can easily calculate the diff based on the last value it has seen from a server, and then push just this diff. It works pretty well. We see that client has modified 2 elements, then it set it to the server. The question is that what server has to respond in that case? So imagine that on the server, meanwhile, one element has changed and it is winning against one of the elements that the client has sent. So in that case, we need to notify the client that actually the one of the elements has changed in the meanwhile, so we can merge it and update its local state. So server doesn't know about the client state of client replica because we don't have a client awareness, replica awareness. So the solution might be to just respond with the fully merged set from the server back, but in reality, actually, most of the elements that that server will respond with back, client already have seen them. So another way to optimize that is to use, we call it scope diff. So when the client sends a bunch of elements, the server will respond only with those values that have won over the elements that client has sent. So actually, in that case, the client will receive only one element that has been updated in the meanwhile, and the only thing it needs to do is to just merge to its local replica. It doesn't care. If all updates had succeeded, then it will be an empty set. The same logic for the client. Okay, so let's talk a little bit about time. So, or I would say the problem with time. So, well, people say that there is no such thing as reliable time, yeah? Yeah, of course, it can be reasonably reliable, but it's a known problem in distributed systems. So I like this quote by Jonas Bonner, actually. He was arguing in one of his presentations that, yeah, when you track the time, actually you are interested in a causality between events, how you can order events in your system. You're less interested in most cases in the actual time value. And this is true. So causality and ordering of events is important. So when we have a let's say concurrent updates to a single element, these are events that we want to order. We want to pick a winner. That's basically we want to order them. Sometimes time can be just good enough. So what is good enough? So I like to think about it like in two cases. The simplest case, of course, when we need to order updates to a single element within a single node, like the node that merges updates to its local replica. So in that case, timestamp for us is just a logical clock, which basically the only thing we expect from it is to grow monotonically. So if you sequentially apply two updates to a single element within a local replica set, you just expect that the order will be the same. The user expects that. So monotonicity is important. And we know that, yeah, if you use naive approach, if you use, I don't know, a GVM, system current time millis, you know that it can go backwards. It's not reliable at all. So in order to ensure the monotonicity, at least what you can do is to employ the +1 strategy that we use. This is a code from our Java SDK. So what we do, we take a max. So we get the timestamp from whatever reliable on a reliable time resource is it, and then we compare it with the just last modified, the previous last modified value +1 to ensure the ordering. Okay, so, and what about the more complicated case? So we need to order updates to the single element on different nodes, happening on different nodes concurrently. That's a much trickier problem, to be honest. Yeah, so of course, some of our clients, we work with navigation devices. Some of them have GPS. GPS clock does provide, in certain conditions, a reliable, pretty reliable clock. In that case, we are fortunate. But what do we do with other clients, mobile clients, and etc.? At least what we try to do is to prefer server time over local time providers, reliable time providers, at least. In that case, so you can do server time and then calculate elapsed time since the last moment when you fetch the local server time, and you get a pretty reasonable timestamp value. I must warn you still, yeah, there might be edge cases. If you have multiple clients modifying exactly the same element concurrently without any reliable time clock, there might be sort of behavior that might be a bit unexpected to the user in a short time frame especially. But it's about understanding these edge cases and thinking whether they are acceptable for user experience and in your domain. So we already seen that picture where we have this unified merge model. Everywhere we merge and diff, awesome. Is there a problem with that? So one merge to rule them all, right? There is a trick. You have to be careful with the merge behavior and with compare behavior. We already talked a bit about it when we talked about timestamps tie. So merge and diff operation have to meet the same output given the same input. So it has to be deterministic, and it has to be the same on all your clients, on all the replicas. So what if it's not the case? Then, if you have a divergence, you might have endless synchronization loops, and that's not fun at all. If your client just constantly thinks that something is not synced, it tries to push all over again. You can kind of mitigate that, prevent that faulty client, but still, it's important thing to pay attention to when you implement a client, especially in this kind of system. So a little bit about takeaways. So what's the point? We kind of wanted to demonstrate that academia is not, academia stuff at least, it's not that scary sometimes as it might seem to like pragmatic devs from industry. Yeah, of course, there is a steep learning curve in some stuff. And in CRDTs as well. If you, for example, go to the Wikipedia page to read what is CRDT, the first sentence that you read actually is that CRDT is a bounded joint semi-lattice. Okay, now I got it. Come on, yeah, it's so easy, right? Yeah, of course, there is this steep learning curve, and we have to collaborate with each other. The research, the industry, we have to bridge the gap. We have to make things more approachable. Because we argue that there are lots of solutions, existing solutions like CRDT, that make implementing these kind of systems and meet your requirements easier than reinventing a wheel. But you have to have a rationale to use these kind of solutions. You have to be sort of like a, sometimes even salesperson when you talk to your industry fellow colleagues. So why should you consider using CRDTs? Why should you consider using free monads, for example? Yeah, it has to be a business value in that. And we also struggled with that at some point because people think that it's too complex. In some sense, yes, but we argue that it solves problems. So if it solves a problem and you do understand limitations and you kind of agree with them, then it brings good results. And of course, it's always about like monitoring how it's actually performing in your real case and constant tuning and improving things. So there is a code available on GitHub with some samples that we already shown and some other ones, including the hour set implementation. It's actually pretty small, like matter of 100 lines of code, something like that. Scala and Java parts, they're completely the same with the amount of features implemented. Yeah, we also put some links and useful like presentations and papers that we found and love really interesting. If you want to know more, just feel free to check them out. There is a lot of going on in CRDT space nowadays. It's kind of becoming a hype. That's true, but we still need to bridge that gap and make it a little bit more approachable because there is still this difference between the awesome research that's happening and actually the understanding how you can apply that in real industry systems. So given that, yeah, the slides already available on speaker deck. So any questions? Thank you. Thank you.
Given how scary it can be if the implementation of the merge functions do diverge, how do you actually guarantee, like at what level are you confident that the implementation is actually correct, and how do you guarantee that?
So, you want me to answer? Yeah, okay. So, yeah, that's the important part. So we have, as Nami mentioned, we have a number of SDKs and reference client implementations. So we have sort of a bunch of standard reference tests that we have to write to verify the merge behavior and compare behavior, which we basically just replicate to different platforms. Another thing that we did lately is that to minimize the diverge, we kind of started migrating to a single C++ based implementation of the core, and then just using that in different mobile clients like Android, iOS, and others. Of course, we also expose REST API of our server. So if you, like a third-party developer, want to integrate with NavCloud, you will have to implement merge correctly. Yeah. So we will prevent the faulty clients to impact the stability of our servers. We have rate limiting and this kind of stuff. But of course, you have to implement yourself these reference tests that verify that. And yeah, we have rigorous testing in different stuff like end-to-end tests that verify the correct convergence in the situation when your device becomes offline. We have, of course, also integration tests and unit tests. The spec for merge and compare is not that big, actually. Reasonably small, I would say. But yeah, you have to implement that on different platforms if you don't share the same common core.
If I want to add something, that it's really good use case for property-based testing. Property-based thing, you can prove that things are working for you. So that's really good use case.
Yeah, actually, on the GitHub page, I already created an issue, the first issue that's to leverage Scala check for that. Because, yeah, we don't use property-based testing in our code base yet, but yeah, it's really appealing use case for that. Absolutely.
I had a question. I was wondering if you could clarify what you meant by choosing the server clock over the client. Like, are you rewriting the timestamp as it comes in to the server from the client? And if so, doesn't that potentially introduce false concurrency if, for instance, do you have clock skew? Or could exacerbate false concurrency?
So, yeah, you mean rewrite in the sense, yeah, exactly. So we prefer, if we can't get a server timestamp, we would prefer to get it if we don't have, for example, GPS reliable clock, yeah, in that sense. Yeah, so, yeah, that's the sense that There is this edge case, yeah. With what do you mean by false concurrency, first of all? So just to clarify.
Like running a merge function when is not necessary.
Okay.
Like because you're falsely detecting two conflicting writes, as you're detecting something falsely as being concurrent.
Okay. Um, why is an issue basically? Like if you run again the merge function,
I don't know. The reason I'm just asking is because in React we observed that with extremely large sets,
yeah.
that reading the object into memory and performing the merge and writing the merge back, if is unnecessary because the object is actually equivalent, is extremely expensive. And so sometimes you can optimize that case by storing a vector clock outside of the CRDT.
Yeah, that's true. So yeah, it's a vector clock, exactly. So, for example, you can also prevent unnecessary reading from the database. In that case, if you have a vector clock, if you sort of compare that it's the same, yeah, that's true. Actually, when we were starting with that system, we were basing on we were also only using the vector clocks. So the first pieces of APIs were implemented with vector clocks that were basically like attached as a metadata to the synchronizable entities, and then we were just passing them over, and then exactly we could detect that if vector clock hasn't changed, then you don't have to do anything. It's true that you have this unnecessary loop always, yeah. So we kind of ignore vector clock now in that sense. At least we will always go to the database. We get the CRDT set. We get it back when it maybe it's not important. Yeah, it's I would say it's a field of optimization in that case. Yeah. There is.
A very quick question. Was the precision of timestamps, is this the nano timestamp or just like a seconds-based timestamp?
It's millis, yeah.
It's millisecond, but I don't know whether it's millisecond, but for some cases that we don't have the server time, we keep the offsets of the moment that the action happened and the moment that we want to send to the server, and that is in nano. But in general, the precision is just a little bit use precision, but it's fine enough for our case.
Exactly. So you can increase if you need, but then you will have stronger requirements for your clients. For example, client integrates with our SDK, or SDK asks to provide a time provider, for example. And in that case, the client will be responsible for providing a time provider with nano time precision. Sometimes it's not possible.
And this is some optimization to get the server timestamp. What we do, we get the server timestamp once we have a connection, and then we correlate that by the tick of the client.
Yeah.
And then that's the reason we use nanosecond. For example, JVM provides nanosecond sequence. That is also useful, but precision in general is millisecond.
Okay, next speaker.
Thank you. There was a question there.
Hey, all right. With this thing, would you consider this a state-based CRDT or an operation-based CRDT?
This is state-based.
Yeah, yeah.
It's state-based. We just we are working at the state, but we are sending the difference between the states, between the local state and what we will send last one that we receive from the server. So this is state-based.
Yeah, but arguably you're sending just the update, so you could.
Yeah, we don't send the operation. One sends the difference. So imagine that you have a list of the favorites, and one of them only changed. We send just this one. We don't send some kind of representation of the operation that update this. This is just state, but just the difference between these.
All right, thanks.
Okay, now we're done.
Thank you.
Connected for most of the time. You traveling in the tunnel, you're going somewhere in the farm, we don't have coverage, and you lose your connection. In TomTom case, also TomTom provides SIM card in some of the devices, built-in SIM card, and it paid for that SIM card. So, but these SIM cards should have very low bandwidth, otherwise they will be really expensive. So your bandwidth also really limited. So the data that transmit with the server and client should be really packed. compacted actually. And also because you are most of the time offline, user doesn't want to wait until you get the connection to change the stuff. They want to be able to do things in offline mode. Oh, and the result of this is to have changes which are concurrent, and those changes can be in the conflicting states. Of course, in a distributed system, there is no guarantee for the order. The user doesn't expect any data loss, and user expects that the data converge to the state that he most probably expects. How to deal with this nature? Of course, you can build a lot of logic all over the place to handle this. I doubt about that, but if you also be able to do that, it's really will be unmaintainable code. But as Linus Torvalds said, actually, the good developers mainly solve the problem. Okay, I think I can start. Hello, everybody. Thanks for joining us for this talk. In this talk, we are going to talk about the practical demystification of CRDT. I'm Nami, he's Dmitry, and Didier also had a great contribution to this talk, but he couldn't join. The first disclaimer is that, okay, we are not hardcore academia guys or from academia, or we are not very hardcore distributed system guys, but we want just use some academic achievement for solving a real world problem. Yeah, this is us. So we do everything, and developer in this project in TomTom is a full stack developer doing from this front end to the back end, and also handling the infrastructure. The project that experienced this research is called NavCloud. It's a cloud-based storage service to allow users to seamlessly synchronize trip information between devices, as well as TomTom website, which then you can have your navigation information like favorites, active routes, destinations, all those things, and you can have it everywhere. And TomTom has a lot of customers, of course, and and a lot of devices in the market. All of them gradually will be enabled by NavCloud. So the project should be, the service that we provide should be scalable and available. And because of the these are sensitive information, especially the location-based information is one of the most sensitive information. We have to be really secure and also compliant to the legal requirement. And also because this is a service and it's going to be used in the third-party application, we have to be reactive and do not degrade their performance. These are the technologies that we used on the server and the client, Arca, Spray, Scala, and we deployed on Amazon Web Services, and also we built different set of client libraries to let the clients integrate with our services. This is a nature of the many synchronization. These are the natures of the many synchronization systems. In the ubiquitous computing era, all the connections are really unstable. So you can be for example, in distributed systems, order is not guaranteed, and of course, you can receive events in a different order. But the good thing is that if you receive something from the client and you're just merging in your node, whatever client or server, you have a local state, you receive something from the network, and you just merge. If your merge function is commutative and associative, it doesn't matter in which order you receive those events, because merge function is commutative and associative. And even also in a distributed system, you receive events more than once. Because imagine I send you something, you send me back acknowledge, the acknowledge it will be lost, and then I have to again send to you. So you receive twice. But if the merge function is idempotent, it doesn't matter. It doesn't harm. I just again merge it. And in practice, CRDT is not for just servers and nodes in the cluster stuff. It actually gives the user a very good experience, because if you have CRDT everywhere in the distributed systems, then you can do local changes. And local changes means that user doesn't need to wait until it gets connection. So it can do offline changes always that he wants, and CRDT will promise him that everything's with the data structures level, because data structures abstracts a lot of things from you and can handle all of those logics out of the box. That's the reason that we went we decided to use CRDTs. As I said, CRDTs is a data structure, it's a data type. It has its own algebra. And it's meant to be distributed. So each CRDT instance can have a lot of replicas all over the place, and all of those can be out of sync at some time, and even in the conflicting states. But CRDT knows how to solve the conflicts, and they all will converge to a correct state. How CRDT does this? The main ingredient of doing this is actually a merge function. Merge function is a binary operation between two CRDTs yielding another CRDT, which must be commutative, associative, and idempotent. And I assume that these are clear characteristics. And why does this matter? Because apparently these characteristics is a good match to the distributed systems characteristics.